afternoon, everyone. Welcome to this talk. The title is relatively generic and also probably not the first one you heard of. The title of the program, it says also something about type decision, and that's a bit the aim that we try to use as a technical tool, exact diagonalization, which many of you know, but few use. And I will show you that for this particular problem of watching the spin chain starting initialized with product states and seeing them how they thermalize in the long or a relatively long time limit actually is an ideal playground to use large-scale exact diagonalization, and we find, at least I find, some interesting results. And so the first version of that work is on archive, and most of the work has been done by my postdoc Ivo Macera. Currently preparing a version where we add, not correct, but we add a few results on diffusion constants, also towards the end of the talk. And so I think what we do, for those of you who have some interest in historical question, I think is probably a quantum modern version of the Fermi-Pasta-Ulam Thingu paradoxon, or kind of a problem. And so this is a plot from, I think, Los Alamos report from the time where, I'm not discussing the full curves, but you can basically see that they prepared numerical simulation of a non-integrable classical coupled chain of harmonic oscillators. And what they found is that even though that system at that time was meant or believed to be non-integrable and therefore kind of at the time chaotic and should thermalize, actually that was a system which turned out to lead to I think insights into the CAM theory and kind of integrability for classical kind of such integrable models. And today, I'm not promising you the same thing, but actually studying even rather simple quantum spin chains made out of qubits or spin half degree of freedom and watching them what they do as a function of real time after initializing them with some non-equilibrium initial state is actually quite an interesting problem still today. And so I think many of you are also interested by that question, how we isolated quantum many-body systems thermalize. So this is a long-standing question. You know, this goes back to the founding years of statistical mechanics and quantum mechanics. And there are some motivations from, say, experimental technology, but also I think time-dependent MPS methods made that topic very popular with a lot of interesting results. And what I find interesting as a curious theoretical physicist is that these questions, kind of thermalizing spin chains, actually seem to have relations to black hole formation, information scrambling, random matrix theory, and SYK models. So that's kind of cool because then you still learn new stuff, even if you're old like I am. And then what I basically feel why we thought it would make sense to come late but still do some exact diagonalization is that I feel that there's a common law that, for example, at least for many systems, the ETH, and if you relax the spin chains thermalize is common law. I think apart from, say, MBL and cars, no one is kind of really questioning that so much, or at least for some time it wasn't. But on the other hand, I felt the quality of numerical results in the field are usually, at least regarding this question, are usually when there is kind of compatibility, one claims victory. And this study is a bit different in the sense we really want to push the limits and check for these discrepancies and understand where they come from. And some of them have to do with higher order kind of corrections, that ETH is like an average theory, but then if you, for example, your initial state doesn't have the right thermal variance and the variance is conserved in the evolution, then you'll find systematic deviations. They are captured by kind of corrections in gradients of the energy density, but still you can actually detect them, and you can even check whether the prefactors match and stuff like that. So some of these will be the results of what I report here. I think here, given that many of you know about that, but this is a bit the backbone of how we operate. So we have an initial state, psi 0, it's a pure state. It's mostly a product state for the purpose of this talk. And we have H, which is a constant Hamiltonian, and you have a continuous time translation invariant, so the system has a Hamiltonian, and that's the propagator here. And then we study states psi of t at some time after the quench or this initialization. And then we look, for example, at some temporal averages. So we time evolve the state, we measure some observables. O can be a 1-point or a 2-point function, typically for this talk. Then you can take a time average over the simulation or some time window after the relaxation or after the initialization, and then you can take temporal averages. Then, of course, you can decompose your state psi of t into the eigenbasis, and then you get these matrix elements. And then you can also work with concepts like the diagonal ensemble. And so I think one of the questions of thermalization is, for example, whether this diagonal ensemble is truly what you find at late times in your simulations. But I think that's not so much questions, and indeed we find some kind of agreement with that. And then ETH, for those who don't know it, makes a statement about these particular matrix elements, or even when alpha and beta are actually, here it's alpha alpha, but you can also look at the alpha beta matrix element. And then the ETH ansatz basically says so that these matrix elements actually have like a diagonal part here with a smooth function which depends on the mean energy between alpha and beta. And then there is an exponential suppression here in e to the minus s, where s is extensive. That's kind of the microcanonical or the thermal entropy density, extensive entropy at that mean energy. And then it's the square root of it, so it's divided by 2. And then here we have a smooth function which depends both on the mean energy and the energy difference of the two states, alpha and beta. And interestingly, there's some kind of pseudo-random matrix Rmn, which pops up and gives some kind of pseudo-statistical noise to the problem. And so this is kind of an important formula, because for some of the problems, we rely on those results to explain what we observe. For example, the fact that this is exponentially suppressed here with volume, because this is extensive, that actually is very interesting, because it helps kind of making our simulation results quite precise, because the off-diagonal matrix elements are typically the ones which are kind of responsible for fast fluctuations. And if they are in amplitude suppressed with this factor, that helps to basically get those oscillations away, and then you're only left with some kind of slower modes, which we can then kind of track quite precisely. And then, in a nutshell, in the end, if kind of the diagonal ensemble, basically here, that's kind of the diagonal ensemble. And then if you use ETH, then these matrix elements are actually something like microcanonical expectation values. And if these are then the same as the thermal or the time average and so on, then you would basically call that the system has thermalized, at least in this definition. There are probably others, but that's kind of the one way to look at the problem. And so what's the plan of the new results we're looking at? Because this is all kind of classic by now. So we want to study a one-dimensional non-integrable quantum spin chain for relatively long times and finite but relatively large system sizes using this exact diagonalization technique. So what you actually do in terms of numerics is you use Krylov propagation methods. So we can study spin chains of between 30 and 40 spins, even exploiting translation and spatial reflection symmetry. So this brings the blocks down a bit. Otherwise, the system is not expected to have additional quantum numbers. And so we basically push simulations where the effective block size is say probably a few hundred millions, and some extreme case perhaps even up to 1 billion if it's really required. But most of it is not that large, but still a relatively large matrix is probably in the many million dimensions or hundreds of millions. And then in the first part, we're going to check for relaxation of local observables towards the thermal expectation values and also their deviations for a class of simple initial states. So the initial states will be product states. And this is very much kind of connected to what I just said about the appearance or the relevance of ETH ideas and thermalization. Then we look, as a particular observable, we also look at entanglement entropies of subsystems. And so many of you know that if you're at finite energy density, we expect that the entanglement entropy actually has a volume law, and that the rate of the volume law, so the growth, is actually related to the thermal entropy. And so what we see even in our relatively small blocks we consider is actually there is also an area law contribution. And by itself, it's not forbidden, but usually people don't care that much about it. But it actually turns out that this area law contribution, I mean, it's significant. We can measure it quite precisely. And actually, it's connected to what people have also studied in the past. It's the mutual information between the block and its immediate environment. And so that's actually also a quantity which is, for example, sensitive to phase transitions or to change of correlations, because mutual information is also, I think, a measure in some sense of classical correlations or also quantum correlations. I don't know so much. You probably know about that much better. But mutual information, you have seen it this morning also, is an interesting quantity. And so the volume law and the area law part are actually intrinsically interesting. And if you're not quenching to infinite temperature, but away from it, then actually there's a finite area law contribution typically, and it's not only volume law. And we can see that. And then the last part, that's perhaps the most interesting or controversial part, is that we're trying to understand how the thermal equilibrium, if it's reached, how it is reached in time. And so we find that in these finite systems, and I stress that we're doing simulations in finite system, but relatively long times compared to the typical kind of velocity, if you want to have one, compared to the system size, then we actually find that observables relax exponentially, so they approach their steady state value exponentially, with an exponential decay, and therefore you can talk about the relaxation time for that finite system and that particular observable. And then we put those relaxation times, we study how they depend on system size, and that's a bit unconventional what we find or report. And then we put it in perspective with Tau's time, which would like dictate energy diffusion, because the system is supposed to be diffusive. And in principle, you can also ask the questions about the Heisenberg time, and we have a little plot on Heisenberg time as well, even though that's much longer than what we typically simulate in before that. Okay, so that's kind of the plan. So the setup, just to stress, because there are also experts on competing techniques or complementary techniques. So what we study basically is a finite size system. So here this is space and this is time. And so the space-time volume we explore is basically a finite system. And what the challenge we face is the red one, is that working here as a function of L is expensive because our ED results scale exponentially in cost and memory, compute time cost and memory as a function of L. So that's a bad direction. But on the other hand, we're not so much limited in time. So we can go to relatively long time at cost linear in time. So that's our setup, whereas there are very impressive simulations using IMPS, time-dependent variation principle, or complementary techniques, or similar ones, and they have not much problem working as a function of L. I mean, IMPS is even almost independent of L, and the time, whereas the problem there is that there is an entanglement barrier building up, at least in many typical or interesting situations, and therefore going to long times is very costly or can also be exponentially difficult. And so in that sense, it's an interesting space-time setup that the two methods somehow have different strengths and challenges. I would also like to mention that there are NPO-based methods which work close to equilibrium. So let's assume that if we find equilibrium here in these simulations, then it's of course also justified to directly work at equilibrium like late times, and then you can also like perturb systems weakly out of equilibrium, do linear response or probe for diffusion. And there are very interesting papers on that, and also many people having done that, I guess, are in the audience. But you could say what is missing, so I have not drawn it, but this is the short time picture, and then there's the entanglement barrier coming, and if you're close to equilibrium, so very late, you again have efficient NPO methods, but the part in between is actually difficult to handle, I guess, for matrix or tensor networks methods, at least so far. And so in that sense, we have other challenges, but at least the time direction is not so much a problem for us. So I think a famous paper by now is the one which Marie Carmen and Ignacio and Matt Hastings authored some time ago. And so we're using a lot of the same setup, apart from the numerical approach, but this is a mixed field Ising model. So we have a CC Ising interaction, nearest neighbors only, and then we have two kind of fields. One is the transverse field, which makes the system, with just these two terms, is integrable by free fermions, and H is a longitudinal field. And we use, I think, hopefully the same parameters as them, which is like a slightly detuned from the critical point in the absence of H, so minus 1.05, and the longitudinal field of 0.5. And at the time, I think this was done using a folding MPO method, I think. And there were three different states, a Y plus, a Z plus, and an X plus. So these are product states along these Cartesian coordinates in spin space. So like the same spin axis as here in the interaction terms plus the Y one. And then there was some interesting phenomenology reported. For example, the state Y plus was qualified as being strong thermalization character, which means that the distance between the thermal density matrix and the one simulated would decrease quickly as a function of time. And then there were two other states called the Z plus and the X plus, where at the time one was called weakly thermalized thing, and the other one no thermalization. And something which intrigued me already almost 10 years ago is to understand whether these are really kind of states which do not thermalize at all, or whether this has to do, for example, where they are in the energy spectrum or a limitation of the computational method. And so I will tell you a little bit about that, what we learned. I mean, some of it has been clarified already by people like Lesik Motrunic. They understood that I think perhaps this one is actually close to the spectrum, edge of the spectrum anyway, so it's a state which takes really a long time to thermalize, but will probably ultimately thermalize. Okay, and so what he did on kind of the initial state, I think here, at least in the main part of the paper, only these Cartesian, like X, Y, Z states were probed, I think. But we're trying to do now a more systematic study. I will come to that in a second. But something in the beginning of the project, almost 10 years ago, what I found interesting is that there was a paper by Matt Hastings and one of his students, where basically they pushed the light cone technique a little bit further. And then he published a paper where these full lines without symbols were published, where basically up to bond dimension 512, which is big, but not super big. He was looking at this X plus and here the X minus starting state and looking at real-time evolution. And you can see in these natural units in time, these were up to 20 times of 20, and here even 10. And then what I found is that by pushing ED, up to system sizes of 32 and 34 spins, that actually here on this scale, that the time point where the two largest system sizes shown here start to be visibly different, that's actually a comparable time to where the MPS also starts to differ. So in that sense, I was a bit positively surprised, because I thought that ED would be inferior anyway. But here I got a little bit of hope that perhaps it's actually worthwhile in these particular systems to actually also try to do ED, because it might be not completely hopeless. Okay, and so now let's switch a bit in the thermodynamics mode. So for this Hamiltonian, you can of course do complete diagonalization, get all the energy levels, and then you can calculate the partition function by just kind of plain sums, numerical sums, and then you can get information like the entropy as a function of temperature, but you can also get the energy as a function of temperature, and then you can combine them and plot the entropy density as a function of the energy density, and that's plotted here. So here we have energy density. So here there's a left end of the spectrum. This is the right end of the spectrum. And here on the vertical axis, we plot the thermal entropy density. So it's the total entropy divided by the number of sites. So that's the entropy density. And the green curve are different system sizes on the order between probably like up to, say, 18 or 20 spins. And so these curves show very little, there are different system sizes shown, but you barely can see the difference. And so this green curve basically is if you want, the equation of state, or at least some kind of a thermodynamic potential, which you know from statistical mechanics, namely the entropy as a function of the energy, or the internal energy is a thermodynamic potential. So this is like a useful curve. And if you look at the slope, it's actually the slope, ds over dE, as it's written up there, is basically beta, the inverse temperature. So then you can see that where the maximum, where the curve is flat, is where beta is 0. And here that's almost in the middle of the spectrum. Precisely, it's when the energy density is 0. And then it's interesting to actually plot the expectation value of these Cartesian states, which have been looked at on this energy window, and then you realize that y plus and y minus, because they basically have no x and z polarization, which are the terms which appear in the Hamiltonian, have precisely 0 energy, so they correspond to states which would thermalize to infinite temperature if they were to thermalize, whereas like z minus, x plus, and z plus are actually more far out at the edges of the spectrum, so do not correspond to like high temperature anymore. I mean, Z minus still does a bit, but X minus and the other two are already quite far out. And something which I find also is interesting to note is that this Hamiltonian, actually it matters mostly where of the sign here of the Ising interaction actually matters, because depending on which side of the spectrum you are, determines whether you're actually like favoring ferromagnetic or antiferromagnetic interactions, basically. And what is important also is that the effect of the transverse field does not matter so much whether it's ferro or antiferro, but the role of the uniform field, because this is always uniform, it's not staggered, it's always uniform, but the role of this term actually matters whether you're on the probing the physics on the ferro or antiferro side. Because on the ferro side, this is like basically coupling to the order parameter, which is like a very relevant perturbation in a conformal field theory sense if there's a critical point close by. Whereas if you have a staggered, if you have the antimagnetic model, then applying a uniform field is not a relevant perturbation, and so the phase actually survives. So what that means, if you put all the signs right in, is that this side here is the sign, the point, the blue point is the parameter chosen. On the antimagnetic side, it's actually that you're relatively close to an Ising CFT transition between an Néel antiferromagnetic order, which is like here around in the whole domain, and the blue point is not that far away, and it's also only detuned by the thermal perturbation and not by the sigma perturbation. So here you can actually expect that at this point, even in the ground state, you're relatively close to a quantum phase transition with a sizable correlation length. I mean, it's finite because you're off criticality, but it's still not that short. However, on the other side, here you're on the ferromagnetic side of the model, and then even though, like by eye, you think the blue point is quite is far away, so indeed you're quite off criticality. But furthermore, you have a sizable longitudinal field which like gaps out your ferromagnetic model quite immediately, and indeed the correlation length here is very short, and this is almost a product state as a ground state which is aligned with the field you impose. So kind of. It's pedestrian what I tell you, but it still kind of matters that this is not completely random, and the fact that this point is close to criticality, we see traces of that, for example, if you study X plus, then the physics is actually to some extent quite different than on the other side of the spectrum. So there's not kind of a quantum chaotic system does not automatically mean that the model is boring and has no structure, but actually there is stuff in it, and it matters where exactly in the parameter space you are. And then, okay, this perhaps I can skip, but the idea is now that we work with product states like Marie Carmen and collaborator did. So in the most of the talk, we always start with the initial state, which is a product state, single side product state. But what you can choose is basically you can choose freely which points on the Bloch sphere you consider. And so the gray domain here, if you can see it, this is basically the whole region of energy here on this axis, and also of variance of those product states with respect to the Hamiltonian on the vertical axis. So this is already kind of a non-trivial shape, this gray region. And so if you take any point on the Bloch sphere, then it will somehow result in an energy density and the variance which lies on this in this gray domain. Actually, the structure is even more complicated. I think there's a part of it. This is actually multi-valued, so there are two different states which give rise to the same variance and energy density. And then the orange points are the ones where we did more or less extensive simulations, because we cannot cover all of it. So we put a lot of orange points. These are the ones used for simulations. And actually, as it turns out later, one interesting aspect is that the black line, that's actually the thermal variance. Like if you take a canonical approach and you look at what is the energy fluctuation density, then you get this black curve. And for reasons which I think I already might have mentioned, is that it actually turns out that if your initial state has the variance of the thermal ensemble, then that's actually a good state, because then the finite size corrections to approach to thermalizations are suppressed. And that's why there's a series of states which we call A4, B4, Z4, and so on. So these are states which are, to relatively high precision, fine-tuned to the thermal energy variance, whereas there are other states which are further away, so they have a variance which is not the one of the corresponding to the thermal ensemble. Okay. And so now let's start reporting actual results after this somewhat long introduction. And so what we do now is first I would like to show you two things. So this is some observable O of t plotted here on the vertical axis. And if you're interested, that's the observable. So it's a 2-point sigma x correlation function, but it doesn't matter so much for the discussion exactly what it is right now. So we start from the y plus product state. So remember, that's a state which has zero energy. So it's a state which should go to the infinite temperature state. So infinite temperature means that actually all Pauli expectation values vanish. So that's why the dashed line here at 0, that's meant to be the thermal expectation value. You don't even have to switch on the computer. It's obvious that that's the limiting value. And then what we show here in the inset perhaps first is these are the finite size results from from 20 spins up to 34 for this particular quench, and this observable shown on some time window. And the first aspect I would like to show you is that if you work with 20 spins, which most of you can do on a laptop or so, you should actually notice that this brown curve, at least on the scale shown here, like fluctuates wildly. Whereas if you push system sizes, then you can see that these curves get smoother and smoother. And for 34, there's still a little bit of wiggling, but the wiggling is like orders of magnitude reduced compared to smaller system sizes. And that's basically where I claim that doing large system sizes really pays off, because actually analyzing and trying to get some physics out of a smooth curve, which might perhaps only have hydrodynamic behavior or whatever to be uncovered, but you're much better off looking at smooth functions than looking at wildly oscillating ones, because the precision or the resolution you have on functional behavior is just much more limited at small system sizes. And so this is the same data shown basically here in some window. And here you can also see that the 20 site results like fluctuate a lot. But on 34, your curve is actually much smoother. And that's we think is a real advantage. Yeah. Why are you asking? I mean, yeah, I think it depends on which observer. If you assume that the system is diffusive, a Thouless time is probably somewhere on that scale or even beyond, we believe. But if you think that there is some modes which are ballistic, then it might already be that the first time the system, like some signal hits the boundary, probably already somewhere here. But this is the thing to be understood. I don't have an a priori assumption on this, but you're right. I mean, there could be a speed of light or some propagation velocity, and it's relatively fast. So this is not. I mean, this is already where the signal might have traveled already several times across the system. But that's what my space-time plot already said. Like we look at long times, we don't bother so much. I mean, many things can happen, but we just look how far we get, and so far we actually just kind of randomly chose to mostly simulate up to times 100, but also because of cost efficiency and such considerations. And we think that that's a good window, but of course we can also go longer, but it gets more expensive. Yeah. Yes. Sorry, I think these curves might actually have been displaced, or they are in a window where indeed they are not on top. If you look at very short times here, the curves lie actually on top of each other. Here.
Yeah, so the first
Yeah, let me check why that is not the case. But I mean, but it's actually also true that some of the things. I mean, if you go back to perhaps let me show that. No. But if you look at that, I mean, this gives a part. I mean, it's not the same state. But for example, if you look at this plot. Here, for example, it's a different quench. It's X plus. It's not the state Y plus. So it's not at all the same situation. But if you want to get the feeling where things start to change, for example, here at time 7, 34 and 32 are starting to deviate kind of quite significantly. Yeah, okay, but yeah, but I think there's nothing wrong with the simulation. Either it means that something has happened there, or it's an artifact of the plotting procedure. Yeah, okay, that I would regret, but I don't think there's a real problem there. But okay, we can discuss this. Yeah, but I mean, this is to this is to define the fluctuations, and indeed the fluctuations is like what I'm highlighting here, but they're not plotted here. So this is the observable itself, but the fluctuations now come on the second slide, and that's like, I think again where it's impressive to see what's happening. So this is a particular observable. So this is now an energy correlator, like I think, an on-site or close neighbor energy correlator. That's what this C0 means. And the thermal ensemble, kind of for the reference value, has been obtained like that. On L tilde means a thermal ensemble. And now what is interesting is that we plot the fluctuations, like how much there is kind of noise on top of the average, and then we plot it on a logarithmic scale for a linear scale of system sizes. And I think what I find impressive is that for 16 sites, you have like these variants of the observable of, say, 10 to the minus 5. And then if you actually crank up system size and you look at the same observable at 34, then you're down to 10 to the minus 10. So you have a gain of 5 orders of magnitude of fluctuation squared. And I think that's impressive. And that's why I call this, there is some high precision aspects in it. So we can really kind of look at fluctuations, temporal fluctuations, which are suppressed by several orders of magnitude. And I think that's quite useful. Okay, and so now we're back to this plot where beyond this fluctuation business being suppressed, but otherwise by eye you can see that the 34 curve actually goes quite close to the dashed line, at least visually, which is the one you expect for infinite temperature. So you could say visually this converges to what you expect, what is the thermal prediction. But now we can do another simulation. We take the Z minus state, and now it's just a local sigma C expectation value. And so if we do that, then of course there's also fluctuation suppression, but we had that's not new. And also I think here we only go up to 32 spins. But what you can see now is that there seems to be convergence in time. So because here it's relatively flat, there's still a little bit of fluctuation, but that's not the point. But what is really surprising is that if you ask what is the thermal value, then that's kind of, this dashed line is the expectation in the thermal ensemble, and you see indicated by this big fat arrow, there's a visible discrepancy between what is the thermal ensemble doing and what our long-time simulations are giving. And here they are converged in time. I mean, at least here on this time window we studied, there's no simple drift. So something must be happening. And that's basically where the corrections to ETH come in. So here, this is just to show that you can also look at other observables. Some of them match, and others have clearly also on a big scale have quite visible differences. So there's something to explain here. And actually, first we thought we discovered a new thing, but then later we learned by ourselves, luckily, that actually in this review by, I think, Luca D'Alessio and others, I think Markus Rigol and Polkovnikov are also co-authors. They basically have already talked about this. And actually, what is the reason in a short story is that if your observable has a second derivative, so curvature with respect to the energy density, then actually the observable you find picks up a correction term which basically scales with the difference in variance. So what we witness here is that the Z minus state or Z plus, whatever the one we took, does actually not have the thermal variance. And therefore, if you quench, it goes to a steady state, but that steady state is actually detuned. The observable is detuned because of curvature effects in the observable, in the thermal ensemble. And what is also nice is that there is actually indeed this prediction here actually contains the second derivative. This is a thermodynamic quantity. You can calculate it thermodynamically. And here is interesting is that this dashed line here is actually the thermal value of that curve. And here you should be impressed that if you basically plot the data as a function of the difference in the variance divided by 2L, you get a relatively nice collapse plot. And this slope here is actually the one dictated by this one. It's not the fit. And so therefore we basically corroborate that formula in an actual setting that the variance mismatch of the thermal ensemble and the initial state, they actually have visible consequences, and here we basically diagnose and confirm them. And you can also do that for another initial state, another observable. Here the collapse is less good, but it's still kind of, at least for the larger system sizes, it starts to get better and better. Here at least 28, there are quite a number of points, but there are also some other effects which we don't fully understand at smaller volume, where kind of the curve also drifts. We don't have an explanation for that, but at least at larger system sizes, the collapse seems to start to work. Yes? Yeah, there's curvature in the observable. Yes, and so I have to see how I'm doing in time.
5 minutes.
Okay, then perhaps I skip this part of the entanglement entropies, so you can read that in the paper or ask me in the break, but there's evidence for the appearance of this area law contribution, which has to do with mutual information. But now what we would like to understand are timescales for thermalization. Because when I talk to people, some people actually expect that the chaotic system like this actually has a finite thermalization time. Which means if you look at an observable and you watch how quickly it goes to equilibrium, some people expect that actually there's a characteristic time, with which, kind of a relaxation time, with which you converge to that. And there are other people who actually say there should be hydrodynamic tails, at least in observables, which somehow coupled to a conserved mode, which here would be energy or energy density. And so there are different schools or different ideas, and we basically just ask our system what's actually going on. And in a nutshell, what we observe, and this is like one way to show it. So here, this is 34 again. It's a particular energy correlator at a particular distance. So it's not generic, but we will see that it doesn't matter that much what observable it is. It's for the Y plus state, which goes to infinite temperature. And what I show you here is the difference of your time evolved observable minus the finite size average here, which in that case would be 0, I guess. Or no, it's not clear. No, it's something else, but it's the offset or the finite size offset. And then I plot it as a function linear in time. And my point is that this curve, so the dashed part is the part which is not included in the fit, and here the black curve is the part which contributes to the fit. The point I want to make here is that this is quite a clean, pure exponential behavior, apart from the short time effect. And so, at least our statement is, and that I think we document quite well, is that in a finite system, in this time window, we consider there's a pure, there's exponential decay, and therefore we can infer a relaxation time on that finite size system for that particular observable, and it's always the convergence towards the finite size value. It's not the thermal one; it's the finite size value for that particular quench. Then there are also other observables, but we find visually also quite clear exponential behavior. And then what we can plot is, so we can plot this decay rate, we can convert into a relaxation time, so that these are these taus. And what we want to show here is that this relaxation time actually has quite a clear linear trend. So here we show system size on a linear scale, relaxation time, and this dashed line is a linear function. And so we basically pretend that for most of the observables and most of the states, apart from some scattering effects, but the dominant behavior we would like to infer from that is actually that the relaxation time for these types of quenches we consider actually depends linearly. So the relaxation time grows as the system size gets longer. And that's an interesting observation, because I'm not aware that anyone has predicted that, but also it basically contradicts to some extent both of these schools I told you, because those people who think that the system has a finite thermalization time, actually it seems not. The thermalization time seems in the system size ranges we consider seems to diverge with system size, or at least grow. Or it might saturate later, but at least on our system size it doesn't. And for those people who think there should be hydrodynamic tails of diffusive origin, there perhaps you would think that this relaxation time actually is something like a tauless time, and therefore a tauless time, at least if it's attributed to diffusion, should basically grow quadratically with system size, so with L squared. But at least in the system size windows we consider, there's no obvious growth which could correspond to L squared. Like something like this, no? So this, it's not even, it's a best fit, something like that, yeah. But it's so clean linear on a log lin plot that. Yes, clearly, yeah. And so here we also plot, for example, things on an energy axis. So this is some observable. It's again C2 for some reason. So here we plot them on an energy axis labeled by the class of states we use, but that's just to orient yourself. And colors are different system sizes. And apart from some stuff at small systems, otherwise you can see there's actually quite an obvious trend with energy density. So this relaxation time depends on energy density. And curiously, it's kind of the relaxation time is shortest on the left window, where there is kind of quantum criticality, whereas on the other side, the relaxation time starts to grow if you go towards the ferromagnetic end. I don't have an explanation, but that's what the data at least seems to show. And also the slope yeah, I mean, it grows here, and that's basically this linear trend with system size, which is not obvious in this way of plotting, but at least you can see that the largest system sizes, which like are 30, we have a broad range. I mean, they clearly have the largest relaxation times compared to the other system sizes. And I think I should slowly come to the end, but if you want in the post-talk discussion, you can also ask me about diffusion constant. So this is a diffusion constant in units which other papers have also used. So we are also able to, by using inhomogeneous initial states, so now product states which have a different energy density in one half of the system and then another one with an opposite offset in the other half of the system, and this gives you an inhomogeneity in the energy density, and you can look for a Fourier mode, the slowest Fourier mode in space, and look at its relaxation time, and from that we can infer via a Taurus time argument the diffusion constant. And so here we can basically see that this is the infinite temperature case, and we get, depending on the different class of initial states which have the same energy density profile, we get some discrepancy or some scattering, but otherwise we can see that we get a trend which even seems to go downward with time still of some, say, a diffusion constants around 1.7 and 1.8. And that's in agreement with some other MPS-based calculation close to equilibrium for the same model with the same parameter. So surprisingly, even in this brute force ED business, we're actually not so far off compared to competing methods, even for the diffusion constant. And I think with this, I come to the end. And I think I leave you this conclusion to read, but you got most of my message by listening to my talk anyway. And I thank you for your attention.